Okay, so in this video I want to prove the following five integrals, namely that the integral from negative pi to pi of the cosine of mx dx is equal to 0. Okay, the integral from negative pi to pi of sine of mx dx, that's also equal to 0. The integral from negative pi to pi of the cosine of mx sine of nx dx, that is equal to 0 for m does not equal to n, for m equals to n, and does not equal to 0, and for m equals to n equals to 0. The integral from negative pi to pi of the cosine of mx, the cosine of nx dx, this integral is 0 for m does not equal to n. This is equal to pi for m equals to n, but does not equal to 0. And this is equal to 2 pi for m equals to n equals to 0. And finally, the integral from negative pi to pi of the sine of mx sine of nx dx, that is equal to 0 for m does not equal to n, pi for m equals to n but does not equal to 0, and it is 0 for m equals to n equals to 0. These are called the orthogonality of the trigonometric functions. Okay, and these can be a little bit of a problem, or a little bit tedious to prove. So I've gone ahead and done the integrations already. So I will show you, kind of explain to you why the values of these integrals are the way they are. Okay, so let's take, for example, the first two integrals. Okay, so the first integral here, this integral, IA, which is the integral from negative pi to pi of the cosine of mx dx. Okay, we can just integrate this directly, and what we see is that this is going to give us 1 over m, the sine of mx evaluated from negative pi to pi. Okay, and once we plug in the limits here, you know that the sine of any integer multiple of pi, well, that's 0, and this is also 0, so this integral will give us 0. So that's the proof for the first integral. Similarly, the second integral we can integrate directly, so that's the integral from negative pi to pi of sine of mx dx. Once again, if we integrate this directly, what we get is negative 1 over m, the cosine of mx integrated from negative pi to pi. Okay, and once we plug in the limits, here you have to be a bit careful, but either way you will get 0, because the cosine of m pi when m is odd is negative 1. Okay, and this is also going to be negative 1. This is just minus m pi, so this is also negative 1. So this negative 1 minus minus 1, well, that's negative 1 plus 1, and that goes to 0. Okay, and similarly when m is even, okay, the cosine will be 1, and this will also be 1. So that in that case we would get 1 minus 1, which is 0. So whether m is even or m is odd, either way this integral will go to 0. Okay, the third integral, okay, which is the integral from negative pi to pi of the cosine of mx sine of nx dx. Okay, we can write this in a convenient form using the Euler identity, which is e to the I mx. We can write as the cosine of mx plus I sine of mx. And similarly, e to the minus I mx will be the cosine of mx minus I sine of mx. Okay, so this would, if we add e to the I mx plus e to the minus I mx, okay, that will just give us cosine of mx plus I sine of mx plus the cosine of mx minus I sine of mx. So you'll see that the sine terms will cancel out, and we'll just end up with 2 cosine of mx. All right, so if we just take the sum, we divide by 2, that will just give us the cosine of mx. Okay, similarly, if we subtract the 2 and divide by 2i, this will give us the sine of mx. So now what we're going to do is we're going to just take, for the cosine of mx, I'm going to substitute this expression in. And for the sine of nx, I'm going to substitute this expression in, okay, with the m, of course, replaced by n. Okay, so this is what I have done here. So I have just substituted those expressions in. So this becomes the integral from negative pi to pi of these two things here. All right. Now, if we multiply this out, we're going to get 1 over 4i outside. And we're going to get 4 terms here, which all have in the exponent this either m plus n or m minus n. Okay. Now you don't have to integrate all of these terms. Okay. If we just realize that these are all of this form, which is e to the I kx. Here k is a positive or a negative integer. Okay. So all of these terms are of the same form. So we can if we integrate this function here, e to the I kx, where k is an integer, all right, this will give us 1 over ik, and e to the I kx evaluated from negative pi to pi. All right, so this we just substitute the limits here, and then we expand this using the Euler identity. Okay. And once we do that, you'll see that the cosine terms will cancel out, and the sine terms will go to 0 because an integer multiple of pi, the sine of any integer multiple of pi, well, that's just 0. Okay, so this whole integral will go to 0. Okay, so what that means is that anything of this form, okay, evaluated from negative pi to pi, okay, over one period, will go to 0. Okay. So let's look at it now on a case-by-case basis. What I mean by that is, well, if m is not equal to n, this integral will go to 0. Okay. Now, why is that? Because, as we just said, that if m is not equal to n, all of these integrals are of this form. And so when we integrate from negative pi to pi, all of these integrals will go to 0. Okay? So that is for m does not equal to n. For m equals to n, all right, what we get is the following integral. And once again, this goes to 0 because, once again, this is of this form, e to the I kx. Okay? So in this case, you will just have, when m is equal to n, you're going to get e to the I 2mx minus 1 plus 1 minus e to the minus 2mx. Okay, so the negative 1 and the plus 1 will cancel out. That will just leave you with this integral here. Okay, and this integral just goes to 0 because of this. All right, and once again, when m equals to n equals to 0, well, you can just plug in 0 here, and you'll see that this will also go to 0. Okay, so this integral IC, which is the integral from negative pi to pi, cosine of mx, sine of nx dx, that is equal to 0 no matter what m and n are. Okay, so that is the third integral. And similarly, we can do the fourth integral. Okay, as I said, this is a little bit tedious, but it's the same thing. So we write the cosine of mx, okay, using the Euler identity. And similarly, this time this is the cosine of nx, so we write it using the Euler identity as well. And once we multiply this out, we get this very nasty integral, okay? But once again, as I said, you don't have to evaluate all of these integrals, okay? If we just use our knowledge that for m does not equal to n, all of these integrals will go to 0, integrated from negative pi to pi, okay? For m equals to n, okay, so if for m equals to n, this term will give us 1, okay, and this term will also give us 1. So that's 1 plus 1, so that will give us the 2 here, and these two terms will just become e to the 2i mx, and this will be e to the minus 2i mx, okay? And so once again, we have to integrate these three terms, and we can, once again, the integral of this term and this term will go to 0, okay? And this will just leave us with the integral of 1 over 4, the integral of 2 dx. And if we evaluate this integral, we get 1/2 times 2 pi, okay, which is just pi, okay? And finally, when m equals to n equals to 0, well, in that case, this will go to 1, and this will also go to 1. So we will just get the integral of 4 dx, okay, with the factor of 1 over 4 outside. And once we evaluate this integral, we will just get 2 pi here, okay? So very tedious, but very logical. Okay, and finally, this is the last integral. And so once again, we will write this using the Euler identity, okay? We'll write the sine of mx and the sine of nx using the Euler identity. We multiply this out, okay, and this is the integral that we get. And we look at it by case. So does for m does not equal to n, well, all of these integrals will go to 0. Okay. For m equals to n but does not equal to 0, this time you will get this will be minus 1. This will be minus 1, so you will get a minus 2 here. The first term will become e to the 2i mx, and the last term will become e to the minus 2i mx. And once again, the integral of this term and this term from negative pi to pi goes to 0. So this will just leave us with the integral from negative pi to pi of minus 2 dx with a factor of negative 1/4 outside. And this, if we evaluate this integral just goes to 2 pi, and this will just give us pi. Okay? And finally, when m equals to n equals to 0, then of course this will give us 1, and this will give us 1. So that will be 1 minus 2, okay? That's negative 1, and then plus 1, that's 0. So that integral will also be 0. Okay? So that is the final integral. So that proves our 4 integrals there. And in the next video, I will use these integrals to calculate the Fourier coefficients. So thank you.